Good morning and welcome back to Dr. Logic Awkwardly Does Logic. In this video, I want to talk to you about the semantics for system D, the deontic logic or the deontic interpretation of the modal operators where necessity doesn't necessarily imply truth, but it does imply possibility. The whole ought implies can principle. So let me bring up my whiteboard so that we've got some stuff to work with, and I will just write down the characteristic axiom for this system. Now, it's very easy to see how we would be able to make this axiom false if we didn't have any constraints whatsoever on the types of Kripke frames we could look at. Because in order for this to be false, we would have to have some world W where necessary P is true and possibly P is false. Now, possibly P being false, that's just the same thing as saying that necessary not P is true. Because possibility says, well, there is some world that W can see where P is true. But if that's not the case, this means that every world that W can see makes P false. So this is what making this conditional false would look like. Now, if we have a world that doesn't see anything, remember way back quite some time ago, we proved that at a dead end, every necessity formula is true. So if W can't see anything, P is both necessary and not P is necessary. And the way to think about this is that from the point of view of W, there just are no possibilities. So it's like sitting in a dark room with your eyes closed and your hands over your ears. You have no information. You cannot say anything about what could or could not be true. As far as you know, anything goes. So that's sort of the idea of these dead-end worlds. But this also tells us exactly what we need to do in order to make this formula unfalsifiable. Well, it has to be the case that W can see something, W prime, and now these two things that I've highlighted with the arrows would become contradictory because the first one would force P to be true at W prime. The second one would force not P to be true, but that would mean P false. And this is a contradiction. So this axiom corresponds to the notion of seriality, which basically says no dead ends. So no dead ends is the informal idea of it. The formal one just says that for every X, there is a Y such that X sees Y. And we can show that seriality exactly characterizes the logic, the validities of this particular logic. So what we want to do is show that if we have a frame, this frame is going to make necessary P implies possibly P true on that frame, if and only if the frame is serial. So this is a theorem, and now I will prove it. This is an if and only if claim, so we need to do both directions. The first thing I'm going to do is assume that F is a serial frame, but then I'm going to, because I want to then show that this axiom has to be valid on it, I'm going to assume that it's not and derive a contradiction from this. It's basically going to be what we just saw up here. Anyway, assume that F is serial, but that, running out of room. This formula is not valid on it. What this means by the definition of validity on a frame or on a class of frames is that there is some model M and some world W where, okay, I should add this model is a model on the frame that is serial, and some world W such that at that world on this model, the axiom is false. Now, by the definition of truth, this means that either, that would be if the conditional were true, that necessary P is true at W and possibly P is not. Now, we know that F is serial. This means that there is a world, and we'll call it W prime, such that W is related to W prime. And actually, I don't even need the and. This is just what you get from seriality. However, since we've got this fact here, which I will label 1, is since W sees W prime and W makes necessary P true, we can then say by 1, we know that at W prime, P is true. Now, I'm actually going to do a slightly different route of reasoning than I did in the bit where I was drawing the frame. I'm not going to go from the fact that there is a world that W can see that makes P true, and therefore by the truth conditions for possibility, this means you get possibility back at W. So because W sees W prime and W prime makes P true, it follows by the truth conditions of possibility that at W, P is possible. But this contradicts our assumption that possibly P was not true at W. Anyway, I should have relabeled this. This is the direction from seriality to validity. So this is the right select version. But this is what we needed to show. So that's done. Now, going the other direction, I'm going to show that if the formula is valid on a frame, then the frame must be serial. However, I'm not going to do it in that direction. I'm going to do it in a contrapositive fashion. So what I'm going to prove is that if F is not serial, then necessary P implies possibly P is not valid on it. Because then by contraposition, you can switch this around and say, well, actually, then if it is valid, it must be serial. So this is again a conditional. We want to start out by assuming the antecedent. And so we'll say let F be a non-serial frame. Now, what we know is that there is at least one world where the seriality condition fails. This means there is some X such that for all Y, X doesn't see Y, i.e. X is a dead end, i.e. there is a dead end. Now, we don't know anything else about this frame. It could be that it has just one dead end world and that's it. Or it could be infinitely large and all of the other worlds can see various things. All we know is that this world can't see anything, and we know that we have this world. So what we need to do now in order to show that the axiom fails to be valid on this frame is we need to be able to tell you how to define a model that makes it false at some world in the frame. But guess what? It's going to be the world where the condition fails to be true. So we have this dead end, we'll call it W. So now we are going to define M as follows. Now, in this case, it's actually kind of trivial because since W cannot see anything, we already know from our previous theorem that both necessary P and necessary not P are true there, whatever valuation we have. So all we need to do is say, let V be arbitrary. It doesn't matter what truth values P or any other letter is assigned at any world, because our world W here is a dead end, and by the earlier theorem we've proved many videos ago, we know that whatever model we have, necessary P will be true at W, and necessary not P will be true at W, which means that it is not true that necessary P implies possibly P. So other times that we do these sorts of proofs, defining the model is not trivial like this. You have to be able to say where P is true, where P is false, look at all of the different possible combinations. In this particular case, as soon as you have a dead-end world, doesn't matter what your valuation is. We already know that everything is going to be necessary and nothing is going to be possible at that world. So the logic of D is characterized by the set of Kripke frames that have serial accessibility relations, where there are no dead ends. I want to say a little bit about how this corresponds to a notion of obligation, because I received a question about this, and it's a very good question. So I'll stop sharing because we don't need to see all of the math for that. Often, when we are thinking in modal terms for understanding necessity and possibility, you can think of it like, okay, I'm in my world and I want to know what's possible. And so I look around at all of the worlds that are accessible to me, and I use the accessibility relation to try to find out what are the worlds accessible to me. This works if you are interested in things like logical necessity, perhaps physical necessity, gnomic necessity, these sorts of things. But there are other times where the concept of necessity that we are talking about doesn't work in this sort of bottom-up way. What we have when we are trying to interpret our modalities in an obligation sort of fashion or a permission sort of fashion, or even thinking in terms of, say, you might have a doxastic account wherein believing something doesn't necessarily imply it's true, but it implies that it's at least consistent. So maybe you can't have contradictory beliefs. In this kind of context, what we are doing is we are saying, this is what the structure of obligation and permission is like. So we look at what the relationship between the operators needs to be in order to capture our intuitions. And then we can go back and say, okay, if we are using a uniform possible world sort of approach to make sense of this, then what do the frames have to look like? So we kind of go from the modal concept back to the constraints that this would put on the frames. Then when you look at an individual frame, what you have is, okay, I'm in my world and I have various things that I know to be obligatory. In terms of then, I don't then look at what is accessible to me to find out what is possible. What I do is I look at what is, how to put this? I look at what is true in my actual world to determine whether my world is accessible to me. I know this is a bit strange because, like, if it's not accessible to me, how can I look at it? But the idea is, if at my actual world, this obligatory fact isn't true, then I know that the actual world, the world I am in, cannot be a relevant possibility. Because if it were, then that obligatory thing would actually be the case. And so the idea here is less that the possible worlds contain like deontic scenarios that we are trying to evaluate to then find out what is necessary, but rather we use what is necessary or what is obliged to find out what is possible or accessible. So it's important when we're talking about Kripke semantics for these various notions to understand that these kind of the order of explanation can go both ways. And in some concepts, it's going to go one way, and in some concepts, it's going to go another. For some people, this might be an argument against using Kripke semantics for explicating these modal notions. You might be like, if we're going to use them, they need to have a uniform explanatory function, and they don't. And that's fine. If you don't like using the deontic notions to determine what is accessible, as opposed to looking at what is accessible and then determining what has to be obliged or permitted. There are other semantics for deontic logics that you can turn to. I'm not going to be discussing those in, at least not in this series of videos, but they are out there and you can go and find them. Alternatively, and this is kind of the sort of like logician agnostic route that I tend to take, it's like, maybe the order of explanation doesn't matter so much, so long as we have something that works. And it provides us with useful insights about the relationship between obligation and permission, which is at the heart of what we are looking at, because we want to be able to know how can we reason about these notions in a consistent way. So if you've got some semantics underpinning it, you know you've got consistency. Maybe the semantics are a little bit weird, but hey, they work. Use them as a formal tool and don't worry about like what deep meaning they're trying to tell us about the nature of modality or obligation or permission or things like that. So I don't know if this might address some worries that people might be having, or if I've just introduced a whole bunch of new ones, but here's some things to think about. And I've already whittled on for too long for this video, so we'll close it here and we'll come back and talk more about what sorts of things you can actually prove in System D in the next video. Until then, take care. Cheers.